Hello wonderful people, welcome to Cosmology Talks. Today we have Sylvia Wenmackers, who is a philosopher of cosmology at KU Leuven. Today she's talking about extensions or reworkings of standard probability theory right down at the level of modifying the fundamental axioms of probability. This is relevant to cosmology because of the possibility that the universe and its contents are infinite, which opens us up to a few annoying probability paradoxes. These happen to be the probability paradoxes that Sylvia, independently of cosmology, has studied as a very maths-oriented philosopher. These paradoxes aren't resolvable within standard probability theory, so philosophers and mathematicians have developed these extensions and modifications. You, the more down-to-earth cosmologists, might think you can simply ignore these paradoxes and get on with your cosmology observations and effective field theory and model building, but I don't agree. Even questions as seemingly obvious as does inflation solve the fine-tuning problems of the Big Bang run into these issues. Inflation might be true, in which case it is probably eternal, in which case the universe will probably grow indefinitely. I asked Sylvia for this talk because she cross-posted her recent paper looking at the implications of these beyond standard probability theories to the cosmology subarchive, and I found the approach interesting. However, I'm actually re-recording this intro because by the end of the discussion, I found her analysis more than just interesting. In fact, I think I'm now persuaded that some of these probability extensions, although they seem to throw away essential aspects of probability, don't in the end violate anything essential to probability and do solve some of these paradoxes in what feels ultimately to be the intuitively correct way. As you'll see in the video, the multiverse isn't now fixed, but at least one of the usual impediments to dealing with it might very well be. And everything we've always been able to measure still has meaningful predictions attached to it. I'm fascinated to see where these theories could lead if taken seriously by the cosmology community, especially those within the community taking the infinities of things like eternal inflation seriously. Anyway, we recorded this a month or so ago when it was still summer here, and it's now a chilly autumn, so you're about to see me with shorter hair and no beard. Don't get too much of a fright. Enjoy. Welcome. Sylvia, do you want to start by telling us briefly about the paper?
Yeah, thank you. Indeed, I heard about this measure problem in inflationary cosmology. And actually there are problems on two levels. One is that there are infinitely many solutions to the Einstein's field equations. So you might want to ask questions like, what is the probability for one of these solutions to have inflation or eternal inflation? So that is one level of questions about probability, where infinity is in play because there are infinitely many possible outcomes. And the other level is that if you start from a universe in which there is eternal inflation, you might be interested in the probability of that universe having certain physical properties, perhaps a value of the cosmological constant, for instance. And here the issue is that in inflationary cosmology, there are infinitely many pocket universes in the model. So again, there is this issue of probability mixed with infinity. And it happens to be the case that for the past decade, I've been looking at problems of probability in cases with infinitely many possible outcomes, or infinite phase spaces, as you would say in physics. So I was very curious to see how what I've learned in that context, how that applies, if that applies to the cosmology case. So that is where this paper came from.
Great. If people are thinking of this talk or your paper 6 months or a year from now, and there were only two things they could remember, what would you want those two things to be?
I guess the first thing is very general. And that is that when you run into a paradox, a reflex can be that you try to run away from it or choose a different direction. We are trained to avoid paradoxes, they are trouble. But I think paradoxes can also be a great occasion to force us to think about our assumptions, because a paradox shows that certain assumptions we've made up until that point, that they are mutually incompatible. So when you really pay attention to the paradox, it usually doesn't show you just one possible solution, but multiple things you might want to try. So in history, we sometimes see that paradoxes are really the starting point for new theoretical developments. So that's one thing that I think also applies to this case. And the other one would be that if you want to model something in cosmology that is infinite, and that could be many things in cosmology like space or time, or in this case a number of pocket universes, it may be necessary that you use certain parts of mathematics that are not commonly used in physics, because physics is usually mainly dealing with phenomena that remain finite. And to find these new ways of modeling it, sometimes it may be interesting to look at or to talk with philosophers of science or of physics specifically, historians or mathematicians who usually don't apply their work to physics. So in general, if you talk to people who have like a different background and are working on different topics, they might have different ideas about solving things. So that might be another one.
Your mention of not running from the problem is an interesting one, because I think some cosmologists have kind of said, well, inflation has this problem of like an internally inflating multiverse, and therefore you can't deal with probability on it, and so that means inflation's a bad model. But it feels to me from the outside as like, what if inflation is actually true? Saying that our mathematical framework can't tell us what the probability distribution isn't saying that the model is wrong. It's just saying we can't deal with the model. But there's nothing in the like fundamental physics and quantum field theory and general relativity that says an eternally inflating multiverse is impossible. So therefore we actually shouldn't run away from it. We should try and confront it. And
yeah, I think it is valuable that there are different responses to problems, whether they're paradoxes or not. I don't think it's an issue that there are people who run away from it and try new things, and other people who sort of face the problem and they have to try new things as well. I think in general it's very hard to predict.
So long as those two groups are nice to each other.
Yeah, that's not always the case, right?
Okay, great. Thanks for the intro. Do you want to maybe now go into some background details about, especially from the philosophy perspective, why these questions are unsolved? What makes it relevant now? I guess probably not going to come up with, we've just built a telescope that's going to measure this particular thing like we normally have in these talks, but why? Perhaps in the context of something you said earlier, you said you've been working on this for a while and now you wanted to apply it to the measure problem. Were you not aware of the measure problem in cosmology until recently, or is there some idea you had where you thought, this might relate to the measure problem? And why is this still unsolved in 2024 when probability theory has been around for quite a few decades now in its most modern form?
Yeah, indeed. The problem is certainly not new. I studied physics around 2000, so I did hear about inflation and Big Bang cosmology in that context. I never thought I would be working on it, and I didn't know a lot about probability at that time. But actually the problem was already there, so in that sense it's not a recent thing to work on it. So even for the introduction here, I just used a review from 2000, and nothing of essence has changed as far as I know. And even then, it's a summary of earlier results. So the general introductory story about inflation is that the original Big Bang model does explain a number of aspects of the universe as we observe it today, but it also leaves certain things unexplained, like how homogeneous and isotropic the microwave background radiation is. And so there are a number of other features, but the proposed explanation was that the very early universe underwent a period of accelerated expansion that we now call inflation. And there was a proposal for a physical process or phenomenon that makes this happen. And as usual in physics, a field was postulated. So this starts from a false vacuum state in which inflation is happening, so the accelerated expansion is happening, and it spontaneously evolves to the true vacuum state, which is obviously the true equilibrium. Now, this was developed in the late 1970s, early 1980s. Alan Guth proposed it, other people helped to develop it. But it was also very soon discovered that in general, this process leads to something that's then called eternal inflation. And that means that the expansion is so fast, or the acceleration is so high, that process is faster than the spontaneous decay from the false vacuum to the true equilibrium. And that means that if we apply it to what we see around us, we are in a part of the universe where inflation has stopped, but we should expect that in vast regions outside of what we can directly observe, obviously, expansion is still going on, and there are other pockets or bubbles like ours where inflation has stopped. So that is sort of the multiverse picture of the eternal inflation model. And that is the scene, so to speak, where certain probabilistic questions can be asked, because there are several infinities involved. So these are like the two levels of questions that I already alluded to in the introduction. One is, what is the probability that a space-time, a solution to the field equations from general relativity has this type of inflation? And the other type of question is about pocket universes in one such model, one space-time with inflation. Both type of questions are discussed in the literature. Regarding the first question, we've seen titles like The Measure Problem in Cosmology that was actually about this first issue. And then there was a really nice paper from a little over 10 years ago where there were 4 major difficulties that were discussed about space-times and questioning whether or not they have inflation. 2 of them are related to the issue that the measure becomes not normalizable. So 2 of their 4 major difficulties were very close to things I've studied from the perspective of probability. So I cannot solve all these questions, obviously, but some of them are close to things I've studied. Regarding the probability over pocket universes, I think that has been discussed even more widely, and there you find rather dramatic terms like the predictability crisis in one of the titles here, and in one of the papers you also find the multiverse unpredictability problem. So this is widely but not universally seen as really a big issue for inflation theory. Now, in this review that I already mentioned by Alan Good from 2000, he tried to explain this second problem, and he said that in such an inflationary multiverse, anything that can happen will happen, so anything is possible. I think that still needs some footnotes, but okay. And then he said, like, the real issue here is we have to, if we want to predict anything in this context, we really need probabilities. So how do we find a probability measure over the pocket universes? He tried to argue that this is really an intricate problem by saying that if you're interested in a universe having a certain property, the issue is that you would expect in such a vast network of pocket universes that actually infinitely many of them have it, if it is possible at all. So what you are comparing is infinitely many of them have it compared to a totality that is infinite. So obviously that ratio is not well defined, it's meaningless. So we need to find a proper limit operation or regularization to have like numerical predictions about it. Okay, so far so good. And then he introduced a model system, as he calls it. That is actually something I have studied for a long time. And that is the idea of a uniform or a fair lottery on the integers or on the natural numbers. And he says that, for instance, you might want to ask what is the probability that a random integer is an odd number, and many people might have the intuition that the answer is half because they alternate between even and odd. But he says there is an ambiguity here because you might order the integers differently. So what you could do, for instance, is do something like put 5 odd numbers and then an even number and go on like that. Like, for instance, 1, 3, 5, 7, 9, and then only a 2. Then you continue 11, 13, etc. And then if you take a limit of that sequence, the even ones appear in a ratio of 1 and 6 rather than 1 and 2. So here I started to get a bit worried because while it is true that obviously a limit depends on the order in which you take the terms, for the natural numbers, so what he calls the model system, there is actually an agreed upon answer. So number theorists who study this, they sometimes talk about probabilities and they would say the answer is half because the natural numbers come with a natural or canonical ordering. So that tells you how to take the limit, and the other ones are sort of irrelevant to the problem. So then I already started to get interested when I heard about this. And I thought maybe there's something to disentangle here. So what I think gets sometimes mixed up in how this is discussed by cosmologists is that, yes, indeed, infinite limits are order dependent, but within mathematics, within the model system, that doesn't really cause a problem because there is a well-defined order given by the mathematical structure. Obviously, in cosmology, it might be a real issue in the sense that pocket universes, for instance, it's not clear how to order them. In many other areas of physics, the temporal order might be interesting, or like the spatial order or something like this. But for pocket universes, that doesn't really apply, because there is no unique way to order them in time. If you think about it relativistically, they're sort of outside of each other's light cone. So there is no unique way to order them, and there's also not a clear way how to solve that. So there is something there that's really an issue of cosmology. But there is a more specific problem with the model system that is usually brought into these discussions. So if you talk about a random integer, there is really a paradox there. There's a formal inconsistency between that idea of a random integer and the standard assumption of probability theory. And I think it is important to keep them apart, like the more general issue about orders of limits and this very specific paradox, just to gauge like at what level of problem are we talking in cosmology. So that is what I try to do. So in the paper, I basically go to all the assumptions in the standard probability theory, and then there are 4 alternative theories that I discuss to see if they might be of help for this issue in cosmology or perhaps elsewhere.
So here you've drawn 2 vacuum energies that have the same value, but one can conceive of a model, and people have conceived of these models in order to try and kind of explain why the value of dark energy is what it is today, where there are more than 2, maybe there's 10, maybe there's 100, maybe there's 10 to the power of 500 different vacua, all with different values of the vacuum energy density. And the same thing happens, that inflation happens eternally, and there is some probability that we don't know that the field will roll into or quantum tunnel into every single one of these vacua. And then the question becomes, okay, if this is the correct universe model of inflation, has this solved the value of dark energy? Is there a meaningfully large probability that the value of the vacuum we find ourselves in is one that has our value? And then you have to ask all these questions that you're asking of like, well, okay, there's an infinite number of all of these vacua that are occupied. Maybe some of them get occupied more often than others because they're closer to where the inflation is happening, but actually quantifiably answering that reaches these paradoxes. You can't do it without confronting these paradoxes. And then on the other side, the other thing that you were saying is a problem, to again kind of make it more strong about why that's a problem. People want to say that inflation solves the fine-tuning problems of the Big Bang, that the Big Bang looks very fine-tuned, because if you look in one direction, the cosmic microwave background is the same temperature as the other one, and they were never in causal contact within the Big Bang, so how did that happen? If you say this arose randomly, again, not saying this in a very strict quantifiable way, because as you've pointed out, one can't, but if one was to imagine this arising randomly, it seems exceptionally unlikely that a universe the size of our current observable universe would just randomly show up, expanding with almost exactly the same temperature everywhere. It seems just completely improbable. So inflation can dynamically produce such a universe, but then you have to say, well, okay, the initial conditions of inflation, how likely are they? And at that point, you're back in the problem of like, well, how do you say how likely an initial condition is? And you run into the problems you were talking about. So these aren't like abstract, I mean, they are abstract philosophical problems, but they're also real problems that cosmology faces when trying to do its mundane, well, if you can call cosmology mundane, the mundane cosmology job of trying to understand the universe without getting into philosophy. But here, these 2 problems are, like banging on the door, and we can't hide from them. Okay, thanks. Yeah, I think I am at least well persuaded that in this case we could learn a lot from more rigorous probability theory, or as you pointed out, probability theory that goes beyond the, vanilla probability theory in trying to tackle these problems in cosmology. So do you want to go into more details now about what these are and how they work and how they might help us in cosmology?
Yeah, sure. So to explain the alternatives, I think it's helpful to really look at the standard probability theory. To do that, let me start with what is actually this paradox of the random integer problem. So it can be phrased very briefly. So the idea is that we imagine that there is a fair lottery on the set of all natural numbers. So any natural number has the same probability of being the result of this random drawing. That's sort of the thought experiment. And then we wonder how would we describe that with probabilities. And it seems that there are two possibilities. Either we assign probability 0 to each individual outcome, or we assign a non-zero value, whatever it may be. But it turns out that both choices lead to an inconsistency. So if we assign probability 0 to each individual possible outcome, and we take the sum of all of that, well, it's an infinite sum, but all the terms are 0, so the result is 0. That means that assignment, that measure, is not normalizable. But that's one of the assumptions of probability, that it's a normal measure. So the probability we assign to all the possible outcomes together, in this case all the natural numbers, that should be 1, not 0. And if we assign any non-zero number, well, their infinite sum is going to diverge. So again, we cannot normalize it. So that's basically the issue. If you have a countably infinite number of possible outcomes, probability theory does not allow you to assign an equal probability to all of them. If we look really at the actions in probability theory, we can see that those assumptions are there. So this is maybe the scariest slide I have, but it really helps me to then show you where the differences are in the various alternatives. So there are only 4 actions, and those go back to Kolmogorov. In the 1930s, he really did something that was long overdue, namely he gave axioms for probability theory. Probability was developed already in the 17th century, and obviously there was a lot added to it, but it didn't yet have this compact specification of its basic assumptions. And you will see there is some text also before the actions themselves, so those are sort of the preamble, the background assumptions. For instance, we use standard set theory. All the possible outcomes form a set. In physics, you would call that a phase space, and a probabilist will call it a sample space. We don't just want to assign a measure to the individual outcomes, but also subsets of them. So that forms an event space. And then the probability itself is a function from that event space to the real numbers, and it has to fulfill these 4 actions. So all the probability values have to be either 0 or larger than 0. The full set of outcomes has to have measure 1. And if you have 2 possibilities that exclude each other, the sum of their probabilities equals the probability of their union. Now the final axiom is actually the only slightly more technical one that says that this idea of additivity also applies if you have a countable infinity of possible events. So if you add all of their probability up, it should also equal the probability of their union. So if we now introduce the idea of a fair lottery on a countable sample space, it turns out that adding that to these actions is asking too much. That becomes inconsistent. So that is this paradox. And I think it's really helpful to think or to track where the different assumptions come from and what is then the explosive mix that turns it inconsistent. So I think there are three crucial elements coming from the theory itself. One is that we assume to real values. So that means we could either assign 0 or some bigger number, but there are no true infinitesimals in the real numbers. There are no numbers sort of in between 0 and any positive real number. So that is a crucial assumption. So the normalization of the measure, obviously, and the countable additivity rule. Those 3 are coming from the theory, and then there are 2 additional ingredients in the thought experiment. That is that we have this countable infinity of possible outcomes, and that we have a uniformity at the singleton level. And I would say that they are mutually inconsistent, those 2 groups of assumptions. And that is what this paradox tells us. But interestingly, not everybody would phrase it exactly that way. And one person who phrased it slightly differently is Alan Guth. So in this context of this review of inflationary cosmology, he concluded that the very idea of a fair lottery on the natural numbers is in itself sort of paradoxical, is internally inconsistent. So he's also not the only one. I saw another author who is also a cosmologist, Steinhardt, make similar comments. And then more recently, a colleague of mine, a philosopher of science, John Norton, he also presented it that way. But I think that's not really correct. I think only if you assume that standard probability theory is the only way we can even think about probabilities, then maybe you reach this conclusion. But I really see it as this mutual incompatibility. And if you view it that way, that leaves the door open to considering other probability formalisms. So that is why I list 4 of them, and all of them are able to deal with a fair lottery without an inconsistency, without a paradox. So that is what I go through in the paper.
Thinking about this from a scientist's perspective, it's unfortunately difficult to test things because we don't have ready access to infinite sets other than in the universe as a whole. And obviously doing observations in the universe is expensive and takes a long time. But yeah, do these 4 methods come to different answers about that?
The way I see it, the first 3 really are sort of compatible with each other and are different ways of examining non-normalisable measures. So you can use them together in the same circumstances. So I don't really see it as sort of a choice between them. It can sometimes be helpful to use all 3, a bit like as if there are 3 different instruments that you use to diagnose the same situation. And then the 4th one is a bit special. It is weaker in the sense that it doesn't impose that much structure on the problem. And because of that, it is more widely applicable. So there might be cases where the first 3 still don't really give you an answer. They are making too strong assumptions, where this infinite lottery logic is sort of the best you can do. So you still get some answers to probability questions, but not as many as you would if the others apply. Yeah, so the first one, the first alternative, is merely finitely additive probability. And it's really the easiest one if you know the standard one, because you just throw out the window this final, more technical axiom. And this was defended by Bruno De Finetti for reasons that are not related to physics at all. He thought that anybody should be free to assign probabilities however they like, and if they like to think about a fair infinite lottery, they should be able to do that, and their theory shouldn't disallow it. So if that final axiom is problematic, just don't assume it for probabilities. Yeah, in this case, what you end up with is actually something very close to what the number theorists would do, because this allows you to assign probability 0 to the singleton outcomes, and you don't have any rule that disallows that sort of comes apart from the probability 1 at the level of all the possibilities, because there's no sum rule that connects the 2 levels.
I guess from a number theorist perspective that feels fine. From a empirical scientist perspective it feels weird, because we are in one of those vacuums, and to say that it had probability 0 of happening, it happened, but maybe that doesn't actually violate anything within this finitely additive probability model. Something with probability 0 can happen, perhaps.
That's true, but even if we think of like a real interval, and we play darts, so we will at random, like blindfolded, we throw a dart at it, and we could really hit like a real number, then we could use Lebesgue measure. It's already, if it's a unit interval, it's already normalized, and the probability of hitting one individual point on a continuum is 0. So actually in other contexts in physics we are already dealing with that type of problem, that singleton outcomes have 0 probability. And there the reason is that in any case there's no uncountable additivity, so we are used to that situation. It's just that in the very specific case of countable infinities, we do normally have this action there.
But is the dart situation not solved by the fact that the tip of the dart is not, infinitely small? It has some finite width, so when you say it hit a real number, it actually hit an interval, and you can give a probability to a sub-interval of the real numbers. If I say from 0.000001 to 0.00000002, there is a probability. It's not 0, it's very small. So there was a probability the dart would hit where it hit. Whereas with this countably infinite thing, there wasn't some non-zero probability that we would be in that particular integer of the unit. If we'd numbered all the universes, that we would be in that one. So it does feel like a higher level of badness.
Yeah, I understand that sort of in physics you very often are dealing with at least empirically indistinguishable intervals, but maybe there are other examples that you might think of where in physics, although we could not measure it beyond an interval, we do think certain variables are represented by a real number. And as soon as you have a probability distribution over that, you actually are dealing with a case where the singleton outcomes have probability 0, although that doesn't mean they are individually impossible or anything like that. So that interpretation, I think we have to let that go in any case, no matter what we will do with the infinite lottery.
Maybe. I mean, I feel like something that can be empirically measured does become more of a problem because it can happen, whereas something that's just an abstract concept doesn't feel like a problem to give it 0 probability.
Yeah, and also in the paper I have this quote by James, who was also a physicist, and he also was not happy with the Finetti's proposal for slightly different reasons than the one you give. And he seemed to have really taken on board sort of the standard theory and that extra axiom, because he said, do we believe that an infinite number of zeros can add up to 1? And then he says the Finetti seems to have found this devious way of answering yes without seeming to do so. So he was really objecting to this disconnect between sort of the finite level where everything is 0, and then at the infinite scale where it's 1 and there's no real axiom that says it has to connect via a sum. But James was not having that either. So yeah, maybe it's really a physicist's intuition that there's something wrong with that approach.
Does James have a preferred option of the 4?
He used an axiomatization that only had finite additivity, but he seemed to assume that countable additivity came with it for free or something like that, so that you didn't have to put it in the axioms, that it was like even more basic than an axiom that you have to put there. So he seemed very convinced in a way of Kolmogorov axioms, although he thought you don't really need that extra axiom there. It just has to be true. You don't have to assume it in the mathematics. But what I really find interesting is that the Finetti said, yeah, okay, I understand that an infinite sum of zeros cannot add up to 1. I mean, he was a good mathematician, he knew that's absurd. But he said, if you could imagine that it wasn't zeros, but actual infinitesimals that you had there in place, as long as you add up only finitely many of them, they're still infinitesimal, so infinitely close to 0. But if it's really an infinite sum, they might add up again to 1. And this is really an intuition that I share with him. Like these zeros, so when we talk about 0 probability in the standard formalism, I translate that in my head as 0 or infinitesimal, but we don't have infinitesimals in the real numbers. But you should keep in mind that 0 might mean a very, very small probability, and there's just no real number to express how small it is other than 0, which is the closest. So I think of it as sort of rounding down the real value, real in the sense of the true value. And yeah, that is then the theory I try to work on myself to make those infinitesimals explicit. Yeah, when I use the word infinitesimal, I know sometimes in physics that term is also used in the context of like the epsilon delta definition of a limit, so then they are real numbers. So that's a different sense of the word infinitesimal. When I use this word here, I really mean a number that is bigger than 0 but smaller than 1 divided by n for any natural number. And that's really weird because we are not used to having those numbers. So they are not in the reals, and usually they are excluded. They're called non-Archimedean. That means that there is no finite number that you can multiply them with such that the product would exceed 1. That's basically what the word non-Archimedean means. But there are consistent ways mathematically to make sense of that idea. And one interesting way was developed in the 1960s by Abram Robinson, and that's sometimes called the hyperreals. So you can think of them as the real numbers with sort of halos of infinitesimal values around each real number. And that those also include infinite numbers, but we don't need them for probability since we only look at the 0-1 interval, obviously.
And I guess if anyone's feeling super skeptical about this is what the history of mathematics has been, right? You start with you don't even start with the integers. You start with the natural numbers, and then you invent subtraction, so you have to have the negative numbers, and then you invent division, so you have to have the rationals, and then you invent square roots, so you have to have the real numbers, and then you invent the square root of -1, so you have to have the complex numbers. So this is just another step that you invent infinitesimals, so you have to have Robinson's hyperreals. And at each step, it's to solve a real problem. And in this case, hopefully we've motivated you. This is a real problem.
Yeah, and that would be a different talk, but also historically there have been authors who came very close to ideas that were only then formalized in the 1960s. And because the standard way of dealing with the continuum was developed earlier, that is considered standard and the others are non-standard. But I at least think that it's partially contingent how that history of mathematics went. So yeah, who knows how it could have been if the infinitesimals were formalized first. So in any case, what we have to change to the standard theory to make this work is mainly the final axiom. This looks scary. I will not go through the details. I just want to show you and explain you why there are so many symbols there. And the reason is that for the standard theory, I was just using the standard limit to define like the infinite sum and the infinite union. I was just using the standard limit. So what I didn't have to do, because everybody knows this already, is to sort of define on the fly what that limit operation is, because we've learned that long ago. But in this case, why does the axiom look so terrible? It's because we are sort of defining a new limit operation on the fly. And this is a limit operation that can take hyperreal values. And one way of thinking about that is that, so for a hyperreal, you have like the standard part, the real part, and then like an infinitesimal modifier. So the standard real part, yeah, you could also do that with the standard limit. But the infinitesimal part actually tells you about the convergence behavior of the limit. So it gives you more information. Like smaller infinitesimals are related to sequences that converge faster, basically. So that is how you can think of this as how it's connected to the standard operation. So yeah, I'm not going to explain how that works mathematically, but what you can do once you have that type of limit in place that gives you infinitesimal values is be a bit more strict in the first axiom. So you may remember the standard one said non-negativity. So any probability value is either 0 or bigger than 0. But here you can actually say, look, if an event is possible at all, so it's not the empty set basically, then I wanted to have a strictly positive value. And of course, if you have infinitesimals, you can make that work. So that is sort of the strength of this approach. And to me, these two things, the additivity is stronger and the first action is stronger. Those are like really two sides of the same coin. So that is something I've been working on together with a mathematician and a logician for a few years actually. And in this case, the way the probability looks like, what that looks like is actually very similar to the natural density, only the limit operation is different, but otherwise the idea is exactly the same. So that means that we can assign an infinitesimal value to individual outcomes here, and they add up all to 1 if you like, if you take an infinite sum. So that's what it does. So there's no longer this disconnect between like the finite and the infinite subsets. They are connected by additivity.
Can I jump in now to a question that I should ask at the end, but I'm just so excited about asking it that I can't hold myself back. In the actual empirical scientific world, you can't actually measure, it's not that you can't measure, but you can't like rule models in or out just based on probabilities, right? Because if I had the probability that number plates were made uniformly or randomly, whatever, and then I see a specific number plate, the probability of that specific number plate was very, very low, but I'm not going to rule out my model of random probability of seeing a number plate. What I have to do is I have to compare two models, and I have to say, okay, there's an alternative model that all the number plates start with T. Did I see a number plate start with T? No, I didn't. Okay, therefore my random model is actually a better model than that one. So you're always having to compare models. So what my thinking at the moment is that the problem with the measure problem with this infinite number of vacua is that, one of the problems is that you want to say what is the real number probability that our vacuum could be the vacuum. And the idea is that maybe you don't need a real probability for even events that happen. You can have an infinitesimal probability, so long as when you're then comparing models, you're comparing two infinitesimal probabilities, and then you can say that the infinitesimal in model A was twice as big as the infinitesimal in model B. Therefore, my empirical measurement favors model A, even though they were just two infinitesimal probabilities. And before this conversation, I might have thought, no, that's not possible. Everything that I measure has to be a real number. But I'm not measuring the probability, right? Like I'm measuring the ratio of probabilities. And that, in fact, could be a real number.
Right. Yeah.
The same way that, quantum mechanical wave functions have all sorts of imaginary numbers lurking around, but as soon as I actually sit down and make an observation, I end up with a real number. I can't measure for I momentum. I can only measure real numbered momentum, but that doesn't mean that the wave function isn't imaginary. So does that make sense, or am I like way off?
Yes, that makes a lot of sense. And you were comparing across models, but I think it was also related to the idea that many philosophers of probability actually stress that conditional probabilities are usually the more interesting ones. So those can also help you to sort of compare things internally. So if you are within one model and one event has a probability that is twice the infinitesimal of the other, you can look at their conditional probability and that would just be a half, for instance. So yeah, but you were even doing a slightly more complex comparison across models. But I think the idea of looking at a ratio is more meaningful. Sometimes that's definitely something you see in applications of this. That happens, yeah.
Cool. Well, keep going. I'm more excited than I was before, and I invited you, so I was already excited.
There are two other alternatives that we could consider. I will not go through them in as detailed way. So one of them is sometimes called quasi-probability, because here we just throw out the window the normality assumption, which is usually the one thing that distinguishes probability measures from any other measure. So here we're really saying, well, any measure can be a probability measure if you like. Now, that doesn't really work. Like, if you keep as close to the original actions as I've done here, that really doesn't allow you to distinguish much. You will be able to assign measures to finite subsets and distinguish between them, but all infinite events will just have measure infinity. So that's not really the way to do it. But in the 1950s, something like this was developed in a cleverer way. So I will not show it because it looks very different. And the reason that it looks different is that that approach really takes conditional probabilities as sort of the starting point. And that works then because then you can compare two events that would have probability infinity, but you compare them as conditional probabilities. And then they sort of normalize each other, so to speak. So then it makes sense to compare them. And what I've noticed in the recent literature is that some physicists do that. And they do that carefully enough and they get sensible results, although they don't really explicitly use this formalism. They sort of know by experience how to take the relevant conditionals and then they can actually work with non-normalized measures and get some probabilistic content out of it.
And do you mean in relation to the multiverse situation, or do you mean in other physics concepts?
So the context in which I've seen it used was in cosmology, but not in inflationary cosmology. I've seen it used in models of what is called central time. So there are models where they try to have a spontaneous arrow of time without positing a low entropy initial condition by hand. So there are attempts to do that. And in that context, they also have non-normalizable measures all over the place. But I think actually that some physicists know how to do it, even though they don't have the language or the formalism explicitly.
That's another thing that's common throughout history, is physicists just kind of jumping to the conclusion and maybe 98% of the time getting it right, 2% of the time being tragically wrong, and then the mathematicians having to plod along every step rigorously defined and eventually arriving at 98% of the time at the same conclusion and 2% of the time saying, physicist, you got it horribly wrong this time.
Yeah, exactly. But I think in this case they were really spot on. So yeah, I was impressed.
Just actually maybe a quick question about that one. I think you alluded to this at the beginning of this section, but I guess I'm doing exactly what I just described physicists often do, but just it feels like intuitively these two things could be made mathematically equivalent. I mean, I know how weird that sounds to say infinite probabilities and infinitesimal could be mathematically equivalent, but again, if you're only caring about the ratios, so long as the ratios of the two infinitesimals and the ratios of the two infinites are always the same number, real number, these could be, like on some deeper level mathematically equivalent. Is that true, or is that way off? Or?
I absolutely agree. What you could do here actually is also use the hyperreals to distinguish like the plus infinity. You could have infinite hyperreal number that would not just tell you that the standard limit diverges, which this lemniscate symbol does, but it would also tell you the rate at which it diverges. So then there's actually an exact correspondence between the two. You would then use one of those hyperreals as sort of the normalization factor, and then you would end up with the previous proposal. So your intuition is very right. Okay, and then the final proposal is really different. So there is no way to get it close to anything that looks like the standard formalism. It also doesn't have that ambition. So it doesn't use any numbers, so you cannot do addition or products or anything like that. It looks a bit like cardinality theory, but with a twist. So what this does, it uses values that are not numbers. So it's just a set of v's with an index. And the index, if it's positive, it just tells you it's a finite set and what is the finite cardinality of the set. If it is a cofinite set, so an infinite set with a complement that's a finite set, it sort of mirrors the cardinalities. So it says like it is the whole set minus a finite set of, for instance, 3 elements. That would be v minus 3. And then the only sets that have not yet gotten a value, those are the ones that are infinite and also their complement is infinite. Those are the ones like the even numbers or the odd numbers or the primes or actually most sets, most subsets. And those are all mapped to the same value, v infinity. So you get like a range of assignments from finite to cofinite. Those are like finely grained. And then there's like one intermediate value for all the others. Now this was really developed for cases where you know that there are countably many possible outcomes, countable infinity of outcomes, but there is no native or natural labeling. So I don't think it's so natural to get this idea if you start from the problem of like a lottery on the natural numbers, because there you have a native labeling. But I do think it is excellent if you think about pocket universes and you think nothing in physics orders them in any natural way, then this is really built for that. It will not answer all questions you might want to ask about probabilities. So in that sense, it's a weak theory. But on the other hand, that is the strength, because it still applies even when the others are like not suitable because they don't give unique, well-defined answers. So this was developed a few years ago. So I think after this, I just had the 2 questions again and what we can and cannot learn by going through the exercise of introducing all these alternative theories. So for the first question, that was, what is the probability of inflation? We started from the solutions to the field equations. And what is done in that literature is usually there is focus on a very small, actually a measure 0 subset of solutions, which are the homogeneous universes. And that collection, that subset, is called a mini superspace. And there is a technique that they borrow from statistical mechanics to define a well-motivated measure on that. At least in the original context, it's well-motivated. So the technique is give first the Hamiltonian formulation. So that's the right way to use or to introduce the parameters of the problem. And if you then apply the Liouville theorem, you will find a measure, which in this case is just the Lebesgue volume of that subspace, that is stable under the dynamics. It's not entirely clear whether that approach applies to our problem at hand here, but okay, let's step over that for a moment. We have a measure that's called the Gibbons-Hawkins-Walker measure, and that is not normalizable. So there you have a typical case for using one of those alternative theories. Now, there is something in addition that is discussed in this literature, and that is that the reason it is not normalizable, the divergence is related to the flat universes. So the measure really blows up around the region of universes that have no spatial curvature. So it's interesting to see that different authors have responded to this differently. So one response was, well, cut out that area and then you don't have the divergence anymore. And later authors like Sean Carroll, they say, no, you have to pay attention to the measure. That tells you that actually most of the universes are flat or nearly flat. So I thought it was interesting that even in that case, which I don't think is that closely related to any of these paradoxes that we discussed before, there are like different responses to what you do when you encounter an infinity in your model.
Is it possible to give a heuristic understanding about why it blows up for flat universes?
Yeah, so the measure is a power of the curvature. I think it goes like 1 over r to the power of 5 over 2 or something like this. But like a more physical understanding, no, I don't know.
Okay. I mean, that makes total sense then, that as the curvature goes to 0, that blows up. So then can you give an explanation for why that was a sensible measure in the first place? Why the 1 over the curvature is something they thought was a good idea?
Well, it comes out of this recipe with the Liouville theorem on the phase space. So it's not built in by hand how it should depend on the curvature. That's sort of discovered from from these assumptions that are imported from statistical mechanics, basically. Okay, and then I tried to think like what is like the order of magnitude of the issues here. So obviously the point where they encounter the measure that's not normalizable, I would say, yeah, that's typically random integer toy problem behavior. So there you could consider using a different theory. But the real issue is here that also on these solutions to the field equations, there's not really a natural order. So I do think that the infinite lottery logic, so the weaker system, might be an answer here. But in a way, this is not the deepest problem in this context. So the issue was, how did they end up with this measure in the first place? Not everybody agrees that this is it's okay to do that. So the idea is that this measure preserves the volume under the dynamics. But what we are doing here is, really think about initial values, if you like, of the universe in a sense. And it's not clear, or maybe it's actually clear that it's not determined by the dynamics. It seems like a very different type of question, like what is the probability of that type of universe? Why would that depend on the dynamics on the space? It's not clear at all. So people who have studied this, some of them are very pessimistic that this technique that comes from statistical mechanics, where it does make sense, that it even applies here at all. And if you don't have that, you don't even have a well-defined measure to start from. So you don't get to the issue that it happens to be not normalizable. So the measure problem occurs earlier. And then, of course, the whole issue with this measure only occurred within, as I mentioned, a measure zero subset of all possible universes. And even if you want to be close to those, it becomes a system with infinitely many degrees of freedom. So there are other infinities to worry about, and I don't have any solutions for those. So if I can offer something, it's sort of at the lowest level of the issue, and I think there are bigger problems before you even get there. So that is for the first question. Maybe not very satisfying, but as a philosopher, I'm used to not knowing the answer a lot of the time, so I'm not too bothered about it.
I think, from the empirical scientist side, it is frustrating, but it's the problem of cosmology, right? Like, it tries to be so fundamental that you find yourself trying to empirically ask what the probability of the beginning of the universe. It's not something we have tested in our ordinary realm very often. We've tested initial conditions, but then they're always like built on something that came beforehand that we can understand and say, I guess it's conditional again. Given these more proto-initial conditions, what would the initial conditions of a system that came from that earlier proto-system be. But somehow, despite that, it still feels very intuitively true to me that the initial conditions to get inflation going are more probable than the initial conditions to have the Big Bang without inflation. Somehow that just still feels intuitively true. The initial conditions for inflation, you need homogeneity and isotropy to like 1 part in 10, but then in the current universe it's 1 part in 100,000. It just somehow one wants to be able to quantify those statements, even though when one sits down and tries to, it all evaporates. But yeah, somehow it feels like there should be an answer. But yeah, maybe as a philosopher you're more used to just asking questions and feeling comfortable if there are no answers.
Yeah, I mean, I would prefer an answer, but I prefer admitting that we really don't know, or maybe sometimes can't know, than having an answer and that's not really well supported. So I rather slow down and then just say, okay, no, I don't really see how you can start answering this, and just admit it, than allowing just an arbitrary model to fill it in. And yeah, so I had like a similar conclusion is maybe too much, but for the second question, I had a similar type of final analysis. So the probability of properties over pocket universes. So the way I described the debate is that some people think this really is a fatal problem, a crisis, and others think, yeah, there's still hope, maybe we will solve it. So I have a few things to add, and I actually think there's also a third option on this list of responses. So first, the people who think it's fatal, they make this comparison to the random integer problem. I really don't think it's closely connected to the paradox, or not that closely. It's really about the order of the terms again, and that is perhaps problematic to define. So then a solution might again be to go to the weaker system of the infinite lottery logic. But as I already indicated, I think there is a third way of looking at it. And yeah, that's a bit strange perhaps, or harder to explain, but we are used in standard probability theory that if we look at an event which has a certain unconditional probability that we might not yet know, we can look at conditional probabilities for that event. And that will give us a range of options, and there is a theorem in standard probability theory that actually guarantees that the unconditional probability lies somewhere in that interval. We can actually compute it as sort of a weighted sum of these conditional probabilities, given certain assumptions. So we're really used to that situation and trained in that situation. But all the alternatives that I've shown, none of them guarantee this in the infinite case. So it might actually happen that the conditional probabilities in one of those alternative theories form an interval or a range, and that the unconditional probability falls outside of it. So that is why, and I haven't done the detailed analysis, but I think that maybe some of these different measures, if you can reconstruct them as different conditional measures, it might not really be a problem that they seem to disagree. They just answer different questions, and they might all be related to the same unconditional measure in the end. So I think that maybe, so I'm not 100% sure, this is sort of a conjecture. I think that some of the measures that are on the market and that seem to fight, that seem inconsistent, if you reconstruct them in one of the alternative theories, they are in the end compatible. And that means that then the measure problem wouldn't be that big as we now usually think. But there is still room for one more comment, or maybe two. One other issue, so like the previous question, there are like more fundamental assumptions that I sort of went along with. And here I find it strange that not many people have questioned this. But so the idea to take the random integer problem as a model system comes from the idea that the pocket universes are countably infinitely many. But that wasn't clear to me at all that is the case. Why couldn't there be uncountably many universes, pocket universes? So it's usually described as sort of a fractal structure. Yeah, on certain models they can tell you the fractal dimension of it. But if you then ask, well, what does that translate to? Like, what type of infinity is that? It's actually surprisingly hard to answer. It turns out that it is independent from standard set theory. It depends on whether the continuum hypothesis holds or not. And if it holds, there would be uncountably many pocket universes. So that would actually mean that we don't run into the random integer paradox, which only happens because of sort of this inconsistency between the countable additivity and the countable sample space. So that would be, sort of an easy way out. You don't run into that paradox if the sample space is bigger. But that seems to be a minority view that is feasible, that it could be uncountable.
I've read a little bit of the cosmology side of this literature, but not a lot. And I'm surprised at what you're saying, because it feels to me intuitive, again, not having thought about this rigorously, but intuitive, that it's not the number of universes that is weighting how likely we are to be in the universe, but the total volume of the universes, right? And volume is then a continuous quantity. Like if I've got maybe there are a countable number of universes, but the probability I'm in one universe should somehow be more likely if it's got 10 times more volume or 10 times more stuff. So the true weighting to me would have felt like it should be related to either volume or density, or not density, sorry, but total amount of stuff, energy or matter or whatever. And that maybe people have simplified it to try it, and maybe that's bad, as you've pointed out, but simplified it to like counting the universes when they thought that the more true thing was just more difficult, but maybe they simplified it and made it more difficult in the process.
Yeah, but of course here, I think that is related actually to this measure problem, because there are many candidate measures and some of them try to do something like that, like look at universes like at a typical time, or there are ways that sort of oversample young universes, pocket universes. And so I think that some of the measures that are on the market, so to speak, they try to do something like that, but then the question really is, how do you compare volume, for instance, if they're not equally old or still have to come into existence? I think that also observer selection effects or universe selection effects, if you like, to a certain extent can be dealt with accurately. I just wanted to point out that that is not something I focused on in this paper, but obviously it's something that interests philosophers of probability a lot. So there are colleagues of mine who have written specifically on this topic, obviously.
Yeah, okay, where to next? This is a question that normally when I'm asking it, I kind of just ask it for the sake of it, and I know what the answer is going to be. It's going to be, we have to do this calculation, we have to wait for the results from this observational study. But I'm actually really intrigued by what you're going to say, Sylvia. Where to next? Like, are you about to collaborate with a bunch of cosmologists and apply some of these ideas to the universe, or is there still work to be done? I have no idea what answer I'm about to hear.
I'm really intrigued by these models about the spontaneous arrow of a cosmological entropic time. So they look a lot like a standard statistical mechanical model for a gas in a box. There's just no box. So it's really simple, and that's satisfying. So the idea is that the boundary conditions that we usually impose on empirical experiments that we do in a finite lab, they don't apply to the cosmos. That seems okay. So then you naturally have again a sample space that is infinite. So these uniform distributions that you would like in order to avoid sort of putting in a low entropy by hand, those are crucial in that setting. And some people have been discussing it. Among them, Alan Good, and he again brought up a paradox, but a different one than the infinite fair lottery paradox, but sort of another paradox that happens downstream from that one. So I have been analyzing that a bit, and I think it's even more informative than in the case of inflationary cosmology. I do think there is more to be gained by using some of these alternative theories. Or at least it helped me understand some of the proposals that physicists are making there. So that is something I hope to develop. And I think, I hope, maybe with the help of this video as well, that these methods with hyperreals, for instance, these non-Archimedean ideas, that they might be applied differently in cosmology, maybe not even related to probability. They think the very notion that there are different scales in cosmology. For instance, if you just think of Ptolemy, He already mentioned that if you look at the distance of the Earth compared to the fixed stars, at that scale you have to treat the Earth like a mathematical point. So I think that's a way of expressing, like, there are the length scales in the cosmos are so vastly different that you need to move to another scale. But these hyperreal numbers, they are very good at doing that. You can model things at different scales, like within the same system of numbers. So I think there are more interesting applications in cosmology. It would be interesting to see if people find those types of applications.
Okay. Well, I guess you can contact Sylvia if you find that interesting. My initial thought would be that I guess so long as the denominator isn't infinity, even though the ratio of the size of the Earth to the size of the observable universe is a huge ratio, the real numbers are still able to contain that. If you were to talk about adding those two distances together, you'd just have a lot of decimal points, and then finally your contribution. But I guess if you do have an infinite universe, so outside the observable universe, then every distance scale becomes a different infinitesimal. You'd have the infinitesimal that even the observable universe becomes an infinitesimal that is just a much larger infinitesimal than the size of the solar system. So yeah, I guess in that mathematical sense it would be relevant, so long as one is not restricting oneself to the observable universe.
Yeah, I agree.
I just wanted to ask one other question. So this is completely outside the realm of cosmology now. It seems to me like a very natural place to apply these is to utilitarianism. I've discussed this with some effective altruists sometime in the last couple of years, and it seems like in their realm they've reached this problem where they want to think about the very, 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 very distant future. So far distant future that in principle, if humanity survives, there may be conscious beings in the universe for forever. I mean, okay, there's the heat death of the universe, but maybe there's ways to overcome the heat death of the universe if you've been thinking about it for 1 billion years. There you maybe do have a finite number of conscious entities, and it does feel then, sorry, not a finite number, a countable number, but infinite of potential conscious entities. And they run into all of these problems when they're trying to make decisions. I mean, I personally feel like they should focus more on the long term being a few thousand years rather than infinite time. But I still think that's where we can actually control the future. But if there's any effective altruists listening, but in any case, if you think about it in the abstract sense of like the infinite future, it seems like this would be even more applicable there, perhaps, because as you were saying, in cosmology, maybe you actually want to think about the continuum things like volumes and densities. But if you're actually making a moral judgment about individual conscious entities, humans, animals, etc., there it doesn't feel like it is so continuous. Do you have any thoughts on that? It wasn't really a question, it was more of a framing.
Yeah, I have thought about it. So I think for dealing with the infinite aspects, these methods are definitely useful. But of course, once you go and think about long-termism and effective altruism, the other important ingredient of the theory is indeed how you deal with risk and utility. And I saw that a colleague of mine, Richard Pettigrew, who is an epistemologist who is based in Bristol, he recently got a grant about studying different theories of risk assignment, specifically for the long-termist application. So I would say if you're interested in that, maybe talk to him in a few years, because the project still has to start. But he's a very careful and also mathematically capable epistemologist. So I'm sure he will have an interesting answer to that.
What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the cosmology community?
Yeah, sometimes when I read about the history of science, and in particular cosmology, I'm sort of struck by the realization how recent most of our knowledge about the cosmos is. And that means that, given I was trained in physics, I am most excited about all the empirical work that is planned now. Even though I work more on the theoretical side, I really think that most of what we know about cosmos today was informed by empirical work. And there's so much that we will know more, like even in 10 years, that I am sort of, as an amateur very interested in hearing about this. I will not be working on it probably myself, because not everything is closely connected to probabilities, but I'm really excited to how much more our view of the cosmos will evolve in that time frame.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this to you, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, check out Jenny Wagner's talk on the cosmological principle. It's a much more empirical take on the cosmological principle, but she does get into the beginning some philosophical definitions of what the cosmological principle may or may not be, and how it's not quite so trivial to define it purely empirically. And other than that, thanks Sylvia for the great talk.
You're welcome.